Hi everyone. So today we're going to finish off with conic sections. So first we're going to look at hyperbolas. So that's the third conic section that we looked at last time. And then we're going to relook at the definition for an ellipse and a hyperbola and how we can go from that definition to the Cartesian form of those two curves. Okay, so hyperbolas. We should all be familiar with the standard rectangular hyperbola. So the rectangular hyperbola. Okay, so that's something like this. We've got our Cartesian axes there, vertical asymptotes, horizontal asymptotes, and then you've got the hyperbola that exists between the asymptotes, something like that. Okay, so that's the rectangular hyperbola. We're going to be looking at something a bit more general, so we just call it a hyperbola, and that is when these asymptotes are not at 90 degrees to each other. So here they're at 90 degrees. We're going to look at cases where these are at some other angle. Okay, so in general, a hyperbola can look like the following. So, hyperbola. Okay, we've got our axes x and y. Okay, now these asymptotes, the two asymptotes there, they can be at different angles now. So we might have an asymptote like this, and an asymptote like this. Okay, and then the hyperbola is going to be between them as before. So it's going to be something like this. So like there, and something like that there. Okay, so you see that it's very similar to the rectangular hyperbola we looked at before. But now it's a bit more general because these asymptotes can be at another angle. Okay, but everything else is very similar. So we've got your Y-intercepts over there, so they're in there. And then this intersection point between the asymptotes, much like we had this intersection between these asymptotes, we can find that because it's going to be halfway between the two turning points. So we've got Y-intercept, or that turning point over there, this Y-intercept, or that turning point, halfway between them, that's going to be the intersection point between the two asymptotes. Okay, so the intersection point of the two asymptotes is halfway. Okay, much like over here, if we look at, say, this point and this point, then it's also going to be halfway between them. Okay, it's like sort of like a center point to the hyperbola. Same thing here. It's like a center point for the hyperbola. Okay, and then we've got the two branches. So we've got this upper branch of the hyperbola, and we've got the lower branch. And we see that they both go off to infinity in either direction there. Okay, so this one is a hyperbola that's like pointing up and pointing down. We can also have a hyperbola pointing the other way, left and right, much like this previous hyperbola can be in the different quadrants. Okay, we can have a similar thing here. So in this case, we can have something like this. Okay, we've got our x and y axes. Okay, we can put in our asymptotes. So let's say it's something like this. Okay, let's say there's our center point. Okay, so that can move around, of course. So we've got the center point there, and then we can have something like this and something like this. Okay, and then again, these two branches, they go off to infinity like that. Okay, but then just a difference between the two. With this one here, we see that we can find the Y-intercepts. Okay, the turning points are along the y-axis there. Here, the turning points are along x. So we've got one over here, and then the other one will be somewhere over there. So let me just redraw this branch. Something like that there. Okay, and then that will be pointing left and right instead of up and down. Okay, so that's just the general idea of what these hyperbolae look like. Okay, so it's something like this where it's pointing up and down, or something like this where it's pointing left and right. Okay, but let's look at an actual example so we can do the calculations. Okay, so example. Sorry, example. Okay, so we have R is equal to 12 over 2 plus 4 sine theta. Okay, so we're going to use this to try and sketch the hyperbola. Now, notice that the denominator should be something like 1 plus, and then the eccentricity times sine theta. But here we've got a 2. Okay, so we need that to be a 1. So let's divide top and bottom by 2. So R is equal to 6 over 1 plus 2 sine theta. And we see here we've got an eccentricity value of 2. So E is equal to 2. It's greater than 1, which means we're dealing with a hyperbola. Okay, good. What about the directrix? So we've got the value of E. The directrix we can find using this top value. Remember, that is going to be E times D. So here we have a directrix value. D is equal to 3. Okay, because 3 times 2, that's going to give us 6. So D is equal to 3. Okay, so that's the value of D. If we wanted to know the equation of the directrix, we just look here. It's plus sine. So we know that the directrix is going to be Y equals plus D. If this was minus sine, then it would be Y equals minus D. Okay, like we went over last time. So the directrix is given by Y is equal to plus 3. Okay, so we can start finding the pieces or the intercepts, and then we can use that to sketch this curve. Okay, so it's going to look something like this. If we put our XY axes, we know the directrix is at Y equals 3, so we can just sketch that in here. Okay, Y equals plus 3, that's our directrix line. Now, if this is the directrix line, then we know that the hyperbola is going to look something like this. We're going to have an upper part and we're going to have a lower part. Okay, where the foci are somewhere up there, somewhere down here. Okay, so that's the rough idea. Okay, we're not going to have the hyperbola cutting through the directrix line. Okay, much like how the parabola doesn't cut through the directrix line. It's either above the line or below the line, but there's no cutting through it. Okay, so we know roughly what it's going to look like. Okay, so let's see what these intercepts are going to be, and that will let us plot this a bit better. Okay, so let's see what happens if we substitute different values of theta. So the theta values that give us the x-intercepts are going to be when theta is 0, so we're on that side, and then on the other side when theta is pi. Okay, that's going to give us the 2 x-intercepts. Okay, so let's see what that's going to be. R of 0, sorry, not theta, R of 0 is going to be 6 over 1 plus 0, so that's just going to be 6. R of pi that's going to be 6 over 1 plus 0 again, so that's going to be 6. So at 0, theta value, radius 6, we're going to have an x-intercept. So let's say that's somewhere over here. So that is, x is 6, y is 0 in Cartesian coordinates. Then the same thing on the other side. When theta is pi, we're on the flip side, radius of 6, so we're 6 units out. So in Cartesian coordinates, this is going to be -6 and 0. Okay, so we've got the two x-intercepts. What about the y-intercepts? Well, that is going to happen when theta is pi over 2, so we're looking in positive y direction. And also we need to look another y direction, so that's when theta is 3 pi over 2. Okay, so r at pi over 2, what's that going to be? So if theta is pi over 2, sine theta is 1. So we have 6 over 3, so that's going to be r equals 2. Okay, and then r at 3 pi over 2. So sine of 3 pi over 2, that's going to be -1. So we're going to have 6 over 1 minus 2. So that's 6 over -2. 6 over -1. So that's -6. Okay, so that's going to give us the two y-intercepts. So the first one at pi over 2, r is 2. So we are 2 units up. So somewhere here. So that's going to be 0, 2 in Cartesian coordinates. And at 3 pi over 2, we have -6. But remember, -6, we flip our direction. Okay, so we flip the direction. So instead of going 6 down, we need to go 6 up. So that's going to be somewhere up here. 0, 6. Okay, so that's because of this minus here. So if we get a minus radius, we need to flip the direction. So instead of going at 3 pi over 2, which means down, we flip it. So we go up 6. So we're over there. Okay, so that's all the intercepts that we've got there. Now we need to find the asymptotes. Okay, so these were the intercepts. Next is finding the asymptotes. Okay, so how do we find the asymptotes? Well, like I said in the previous page here, there we go, the asymptotes, that is when the branches go off to infinity. So the radius value, remember that's the distance to the curve from the origin, that needs to go to infinity, plus or minus infinity. So if we look here, r equals 6 over 1 plus 2 sine theta, we need that to go to infinity. So r equals 6 over 1 plus 2 sine theta. We need this to go to infinity or plus or minus infinity, and that means we have an asymptote. So when we have an asymptote. Okay, now when will this go to infinity? Well, the top is finite, it's 6. So this is going to go into infinity when this bottom part goes to 0. So this bottom part here, that needs to go to 0. Okay, and then that means the whole thing goes to infinity. Okay, so that's the condition for an asymptote. The denominator needs to be 0. So asymptote, if and only if this denominator is 0. So 1 plus 2 sine theta is equal to 0. We can just solve for theta. So 2 sine theta is equal to -1. Sine theta is equal to -1/2. Okay, when does that happen? Well, that's going to be when theta is equal to pi plus pi over 6, or 180 plus 30, if you want to think of it like that. or when theta is 2 pi minus pi over 6. Okay, that's the two theta values where it's going to be minus a half. So theta is going to be 6 pi over 6 plus pi over 6, so that's 7 pi over 6. And on the other hand, we have 2 pi minus pi over 6, so that's 12 pi over 6 minus pi over 6, so that's 11 pi over 6. Okay, so these are the two angles of the asymptotes. So if we look back at this other picture, okay, these asymptotes are at angles to each other, right? Unlike with the rectangular hyperbola where they're just 90 degrees. So there's some angle involved here, angle theta. Okay, that's like the opening angle for the hyperbola. Now, if we want to write this asymptote in a nicer way, we can use this angle to find the gradient. Once we have the gradient, we can write these asymptote lines like y equals mx plus c. Okay, that's a bit easier to draw. Okay, so we got these two angles, let's say theta 1 and theta 2. Let's convert these into gradients, and then that will help us draw the lines a bit easier. Okay, so m1 is going to be tan theta 1. So that's going to be m1 is 1 over root 3. And then for this other one, we're going to have m2 is tan theta 2. So m2 is going to be minus 1 over root 3. Okay, so we've got the two gradients. Now we need to find the y-intercept. Okay, but if we look back at our picture, if you just imagine where the gradients are, the y-intercept is halfway between the two turning points. I think this picture will be a bit better. Here we go. So we've got the top y-intercept. So top y-intercept. We've got the bottom y-intercept. Okay, we see that the y-intercept for the two asymptotes is over here. Okay, it's halfway between the y-intercepts. And that y-intercept is the same for both asymptotes. So we just need to calculate it once. Okay, so we've got the gradients, now the y-intercept. So y-intercept for asymptote lines. Okay, remember, it's going to be halfway between the y-intercepts. So C is going to be 1/2 of the first y-intercept. We calculated that already. That's 6. The other y-intercept was at 2. So it's going to be 1/2 of 6 plus 2. 1/2 of 6 plus 2. 6 plus 2, that's 8 divided by 2. That's going to be 4. Okay, so we've got our two asymptote lines. Okay, so the first one, y is equal to 1 over root 3x plus 4. Okay, so that's like the positive asymptote line, okay, the increasing one. And then the decreasing one will be minus 1 over root 3x plus 4. Okay, that's going to be the decreasing asymptote line. Okay, so we've got the intercepts, we've got the asymptotes. Now we can sketch what this looks like. Okay, so let's fill that in here. Okay, so I'm just going to redraw this so that it's a bit neater. So we've got, looks like this, x and y. Okay, let's put in the x-intercepts. So we found those were at -6 and 0, 6 and 0. So over here, -6, 0, and I'll try and make it the same on the side, 6 and 0. Okay, so those are the two x-intercepts. The two y-intercepts we found were 0, 2 and 0, 6. 0, 2, somewhere here. 0, 6, somewhere here. Okay. And then the center of the asymptote lines, the intersection, is going to be at 0, 4. So that's somewhere here. Let's put that in red. Okay, so the asymptotes are going to go through that line. So the asymptotes will be something like this. Okay, we'll cut through like that, just before this x-intercept, and it will cut it just after the other intercept. So it'll be something like that. Okay, and then we can just connect the dots. So in this bottom portion, we're going to connect the dots. Let's put that in blue. So it's going to be very close to the asymptote. It's going to pass through there, pass through there. Oh, sorry. Let's try to draw that a bit neater. There, there. And then it's going to go off again. Okay, so that's the bottom portion. And then for the top portion, it's going to be exactly the same. So it's going to be very close to the asymptote, but not touching. It's going to come down, pass through the intercepts, and then go back up. Okay. And if you want, you can draw the directrix line as well, but that's not needed. Okay, so we've got, as long as you draw the top branch, the bottom branch, and the asymptotes, that's enough there. Okay, so let's just make a little note. Draw the two branches. Okay, so it might be the one above and one below, or it could be the one on the left and the right, okay, depending on the shape that you have. And then the asymptotes. So I recommend drawing the asymptotes in first, and then you can just fit the hyperbola between the asymptotes. Okay, it's a bit easier to draw the hyperbola after you know where the asymptotes are. So maybe I should put that first here. Draw asymptotes and then draw the branches. And then you draw the branches like that. Okay. Any questions on this? Okay, I've got a question here. It's a bit, so this question is out of the topic. Okay, sure. I'll answer you on the WhatsApp group. Okay. Question's a bit long there. I'll answer it on the WhatsApp group. Okay. So that is how we sketch a hyperbola. Now, I just wanted to go through one thing on going from the definition of parabolas, ellipses, and hyperbolae. So using the definition that we looked at last time and convert that into the Cartesian form that we know. Okay, so let's just go through the three definitions quickly. Okay, and by that, I mean the geometric definitions. Remember the distance from the focus points to the curve, that definition there. Okay, so for a parabola, we have the following definition. So if this is our XY plane, then if we've got a directrix line, we called it L last time, and we've got a focus F, then the parabola fits in something like this, something like that. And the definition in terms of the focus and the directrix line was that if we take this distance from the focus to the curve, let's say at some point P, given by XY, and then we take the distance from that point P down to the directrix line, these two distances are the same. Okay, so using the fact that these distances are the same, we can use that to find the equation of a parabola. Okay, so I'm going to leave that for homework for you to try. So given a focus point, let's say at 0f, okay, and the directrix line, we know that's going to be something like y equals d. Okay, using this information, find the equation for this parabola. Okay, so that's going to be homework. Find equation of the parabola. Okay. Then the second case was if we have an ellipse. Okay, and we can also define it geometrically. Sorry, number one, that's a parabola. Okay, the second case is with an ellipse. We can also define it in terms of these distances. So with an ellipse, we have something like this, X and Y. Okay, so remember the ellipse, we've got two focus points. We've got one over here, one over here. Let's call this F1 and F2. Okay, now you could draw the directrix line, but we don't need it for this case. Okay, we've got our ellipse like that. Okay, and then if we look at this distance here and this distance here to point P, so this is Pxy, then the defining feature of an ellipse is that the distance F1 to P, let's call that F1P, plus the distance from F2 to P, F2 to P, this is equal to a constant. Okay, now we're going to be looking at this next time more on ellipses. But if we just say that this constant is 2a, where this a is a constant, okay, then we can use this fact to find the equation of an ellipse. Okay, so that's also going to be homework. Okay, homework. Find the equation of the ellipse. Okay, provided we know this. Okay, this sum of the distances there is equal to 2a. Find the equation of the ellipse in terms of this a variable here. Okay, so that's an ellipse, and then we can do the same thing for a hyperbola. So number 3, hyperbola. Okay, sorry, I don't know if I mentioned this. This equation here, this is in Cartesian form, right? Because we're working with distances between 2 points, given the Cartesian coordinates. So the equation is also in Cartesian coordinates. Okay, same thing with the ellipse, same thing with the hyperbola. Okay, the hyperbola, we can do a similar thing. We've got two focus points, F1, F2. And then the hyperbola is going to look something like this. Okay. Then we have a similar thing here. So if this is a point P, P xy on the hyperbola, then this distance here minus this distance here is equal to a constant. Okay, so for an ellipse, we added the distances and we got a constant. For our hyperbola, we subtract the distances and we get the constant. So here we get, I said F1P last time, so let's do that. F1P minus F2P is equal to a constant. So let's say it's the same 2a. But because we can swap these around, so here I took F1P minus F2P. If we swap this around, we get a minus sign. So in fact, this is plus or minus 2a. So depending on the order of this, we get a different hyperbola. So one ordering, with, let's say with the plus sign, we get this hyperbola, okay, which goes left and right. If we take the other sign, then we get one that goes up and down. Okay, so there's the two different cases depending on the sign that you choose. so 2 different cases depending on the sign. Okay. Okay, so this is just a different way of defining these curves. Okay, so we've looked at it in terms of the polar form equation, this one over here. Okay, so we've looked at it in terms of that. This is just another way of looking at these shapes. Okay, so we can look at it in terms of these constraints here. So for the parabola, those 2 distances must be equal, and then you can get the equation of the parabola from that. For the ellipse, those 2 distances added together is a constant, and that gives you an ellipse. Or for the hyperbola, you take those 2 distances, you take the difference, and that's a constant. Okay, and then from that, you can also get the equation. Okay, so it's just another way of looking at things. All right, any questions on this, this way of defining these shapes? Okay, so try out these homework problems. I will be posting the solutions later on today, so you can check your work. And then that's going to be it for the conic sections stuff. So next week, we're going to be doing a little bit more on the ellipses, but it's not going to be tested. Okay, it's just a bit of terminology, about ellipses and hyperbole. But for the summative tutorial quiz on Tuesday, it's just going to be up to this part. Okay, so the stuff that we do next week, that's not going to be in that summative quiz. Okay, any questions on that? Okay, cool. So just look out on the Learn 2022 for these solutions, and then you can check your work later on. Okay, if you do have any questions, you can let me know on the WhatsApp group, or you can send me an email. And remember that the tutors are also available if you have any questions. Okay, bye everyone.